In this session, I'll be talking about PV diagrams. As we describe PV diagrams, we'll be in essence describing what we mean by isobaric, isometric, isothermal, and adiabatic processes coming up. So what are PV diagrams? PV stands for pressure volume. So a PV diagram is simply a graph that is used to describe the corresponding changes in pressure and volume of a system. Now let's consider a gas in a container like this one. If I heat this gas, there will be a process that will take place in this gas. This process involves this heat that is coming in, increasing the kinetic energy of the molecules here, and as a result, this piston is pushed up, and that means the system does work against the surrounding. Now likewise, if I push this piston downwards like that, I'll be doing work on the system. Now in both these processes, the parameters like pressure and volume of the gas will change. Now in order to visualize these changes, we make use of what we call the PV diagram. And like I had earlier pointed out, a PV diagram is simply a graph that shows how the pressure changes with respect to volume. Now it's also important to take note that we can know the amount of work done, call it, or the amount of energy expended in a system by simply estimating the area under the graph that we'll be drawing here, like we shall see. So we'll get started with what we call the isobaric process. So now what is an isobaric process? An isobaric process is simply a thermodynamic process. So it's a process that takes place when the pressure is constant. Iso means same pressure. So it's a process that will take place at constant pressure in simple terms. So if we are to draw, if this is a process, of course, when we are holding the pressure constant, if we are to introduce heat here, and this is supposed to be taking place in such a way that pressure is held constant, it means that as heat is coming in, as this gas tends to expand, in order for us to keep this gas at a constant pressure, that is compensated for by this piston being pushed upwards. So as this piston is being pushed upwards, it will be pushed probably from this point A, VA, to that point VB. So let's assume that it is this is the beginning point, the volume. So this volume increases up to VB, from here to here. Since it is an isobaric process, it's taking place at constant pressure. It means that we'll look at the pressure axis here, our value of P here will be the same. So it means if it started from here up to right there, it means this is moving, the graph will be like that. As simple as that. So that is our isobaric process, and if we want to find the amount of work done here, we simply find the area under this graph. And for this isobaric process, the area, if we want to find the work done here, the area, we are simply going to find the area of this, which is going to be the P, let's call this P naught. So it's going to be P times V. As simple as that. And that's an isobaric process for you. So we'll go on to what we call an isometric or an isochoric. Sometimes they call it isochoric. Sometimes they call it isovolumetric process. Now, iso, of course, we say means same, and it's same volume. Isovolumetric. I don't know why they call them these other names, but isometric or an isochoric or an isovolumetric process is just a process that takes place at constant volume. It means that we are having our gas right there, and when we subject this to heat, these particles here will get that heat and their kinetic energy will increase, or their internal energy here will increase. Remember, we are dealing with an ideal gas. So an ideal gas does not have potential energy in between its molecules, so it's simply entirely the kinetic energy of the particles that will increase. But since we are dealing with a process that is happening at constant volume, it means that this thing, no volume will increase. This thing is static. So meaning that this gas, you'll heat it, its internal energy will increase, but it will not do work because it is in a static container. And so meaning that if this is its volume is, that is V1, it's going to remain V1 right there. That is V1. Let's call this V1. And what happens to the pressure? Of course, the pressure here is going to increase because as these particles gain their internal energy increases as a result of increase in kinetic energy, they'll be colliding with the walls of this container more often. It means that the pressure here will increase. Probably it will increase from pressure P1 to P2. And so it means that when we are drawing a PV diagram for an isometric process, it's going to start from there. The pressure was at that point, and that pressure will increase to that point. It's going to be the same volume. So the PV diagram is simply that for an isometric process. Remember, we said that for a PV diagram, the area under the graph gives us the work done. Now here, since the volume is static, there is no work being done, and it's even shown on the graph. There is no area under this graph. So basically, there is no work done when it comes to an isometric process. An isometric process being the process that takes place at constant volume. That's an isometric process for you. Now let's get to what we call an isothermal process. Now an isothermal process is simply, like we said, iso means same, thermal, it's taking place at the same temperature. Isothermal process, it is a kind of process that takes place at the same temperature. So before we draw the PV diagram for an isothermal process, let's try and get to the nitty-gritties of an isotherm or an isothermal process, a process where the temperature is held constant. Now for us to ensure that this system here is operating at such a way that a temperature is held constant, we are going to pull down this piston up and down, or this piston will work in such a way that this gas is held at constant temperature. Now, let's first remind ourselves of the first law of thermodynamics. The first law of thermodynamics, that the heat that is supplied in here is going to be equal to the change in internal energy in there plus the work done by the system. That's the first law of thermodynamics. We all know that here we are dealing with an ideal gas. If we are dealing with an ideal gas, we know that any amount of heat supplied, let's call that Q, any amount of heat supplied is going to go into increasing the kinetic energy of these particles of the ideal gas. And the kinetic energy of these particles that are increasing here is what is causing an increase in the internal energy. We explained that earlier, why it's only kinetic energy. So it means that as it is increasing the kinetic energy of this gas, if there is any work that is going to be done on this system to push this piston upwards, that is work done by the system onto the surrounding, which is denoted by this. But then now we are having a thermodynamic process where when we introduce heat here, as we introduce heat here, these particles are going to increase their kinetic energy. And when their kinetic energy increases, that increase in kinetic energy is what is responsible for the change in internal energy, according to the first law of thermodynamics. But then here we are dealing with an isothermal process. And an isothermal process is supposed to be taking place at constant temperature. Now, if the kinetic energy of these particles is increasing, and it is this kinetic energy that is responsible for the change in internal energy, we all know that kinetic energy is directly proportional to temperature. I mean, the higher the kinetic energy of these particles, the higher the temperature. The lower the kinetic energy of these particles, the lower the temperature. So it simply means that the temperature is also directly proportional to the internal energy. Meaning that if we are to make sure that this system is happening at constant temperature, if it is, since we are calling it isothermal, if this system is to be held at constant temperature, it simply means that the temperature of these particles, or the kinetic energy of these particles, is also supposed to be held constant for us to be able to satisfy this condition that it's supposed to be held at constant temperature. So what does that mean? It means, if you're reasoning with me, that internal energy for an isothermal process is going to be equal to 0. I mean, there is not going to be change in any internal energy. For us to be able to hold this thing at constant temperature, it means that this change is going to be, this won't change. The internal energy is not supposed to be changing. Otherwise, if it changed, it would mean that the kinetic energy of these particles is changing. If the kinetic energy of these particles is changing, that would simply mean that the temperature of this thing is changing, and if the temperature of this system is changing, then it would cease to be an isothermal process. So from the first law of thermodynamics, for an isothermal process to really take place, it means that the internal energy is going to be constant because of the explanation I've just given. So then what does it mean? So that means that if any gas comes in here and it expands and does work on this surrounding, an amount of heat has to be supplied to the gas in order to maintain the temperature, or in order to keep the kinetic energy of these molecules to be constant. Likewise, if the surrounding does work on the system, thereby causing these gases to contract, a certain amount of heat has to leave the system so that the temperature of the system is held constant. If I may repeat this for emphasis, this is what I mean. If this gas is to expand, it expanding means that it is going to lose some work. It's going to lose some energy in the process of it doing work against the surrounding. As it's losing energy in the process of doing work against the surrounding, it would mean that the kinetic energy of these particles is going to drop. And if it is dropping, it would mean that the temperature is no longer going to be constant, it's going to drop. Now, to avoid this temperature from dropping, as this gas is expanding to push this piston upwards, we have to a certain amount of heat has to be introduced into the system to compensate for that loss of work as it's doing work. So as this heat is introduced into the system to compensate for that loss of work, it keeps this system at constant temperature. Conversely, if this piston is to be pushed downwards, if it is pushing downwards, it means that the environment or the surrounding is doing work against this system. If you push it down and this starts doing work against the system, it means that this internal energy here is going to increase because work is being done on the system. If it increases, there would be an imminent threat that the temperature here could increase because the kinetic energy of the particles has increased. So to avoid that kinetic energy from increasing, or to avoid this temperature from increasing, if this system, the surroundings doing work on it, then a certain amount of energy has to be left to go out of the system so that we keep this system at constant temperature. So from what I'm explaining here, this being, since there is no change in internal energy, it means that our Q is going to be equal to the work done. By this I mean that any kind of work that is being done, any work, any Q, any kind of heat that is introduced into the system should be corresponding to the amount of work being done by the system. And the other way around, if there is any kind of work being done on the system, that should correspond to the amount of heat that is being taken out of the system. That is the explanation for this, for the Q being equal to the W, the first law of thermodynamics, reducing to this for the case of an isothermal process. So let's draw the PV diagram here for this isothermal process. We know that PV is going to be equal to RT. Here we're dealing with 1 mole of a gas, so our value of N here is 1. So since it is P against V, let's make P the subject of the formula. It becomes P is going to be equal to RT over V. So if you look at this, R is a constant, and then T, since it is an isothermal process, it means that the temperature is also constant. So you realize that our numerator here is having constant values. So this could easily be translated into being P is equal to 1 over V. So P is equal to 1 over V. It's like drawing a graph of Y, because P is on the Y axis. So Y is equal to 1 over V. V is like X. Now the graph of Y is equal to 1 over X here looks like this. And probably this is moving from here, this from volume V up to there. This is V1, V2. And of course, when we are talking about a diagram like this, for an isothermal process, if you want to find the work done by an isothermal process, we are simply going to find the area under that curve. Now, an isothermal process can be reversible. So from what we've been discussing earlier, you realize that when this gas expands and pushes this piston upward, some heat is supposed to be coming in to compensate, to keep the temperature constant. Likewise, if I push this piston downwards and this gas is compressed, some heat is supposed to leave the system to maintain the kinetic energy of the molecules here. So what does that mean? It means that if I push this piston up and down very fast, it means that let's say I'm compressing this gas and I push this thing down very fast. Pushing this piston down very fast means that I am not going to give enough time for heat to leave the system. If I have not given this heat enough time to leave, because heat does not move so fast, it takes its time for it to leave. And likewise, when I pull this thing up, heat will take its time to come in. So if I move this piston very fast, then I won't be able to have an isothermal process. Why? Because the temperature of the gas will increase as a result. So this brings us to the first condition for an isothermal process to take place. For an isothermal process to take place, you have to move this piston very slowly. You push it very slowly. Why? Because you're giving enough time, you're giving this heat enough time to come out. You push it very slowly to give this enough time to flow out. Likewise, if this gas is to expand and you pulling this piston up, you're supposed to do it very slowly so that you give this heat enough time to flow back in. So that's the first condition for an isothermal process to take place. The piston has to be moved slowly to give enough time for that heat to conduct either into the system or out of the system. Now, the second condition for an isothermal process to take place is that these walls must be thin and they must be good conductors of heat so that heat can easily be conducted to and from the system. Then also the walls, these ones, have to be surrounded by a constant temperature reservoir. Maybe you get this container and you put it in a basin of water that is at a certain constant temperature. So we surround this by a constant temperature reservoir, and all this is in an effort to maintain a constant temperature in the system, since we are dealing with an isothermal process. Now, these are the conditions that are necessary for a reversible isothermal process. Now, by reversible isothermal process, I mean a process that can be taken from the final state to the initial state by retracing the steps that caused it through very small changes. Or I may say that by definition, a reversible process is a process that can take from the final state to the initial state by retracing the steps that caused it through very small changes. Meaning, for a process to qualify to be reversible process, pressure, volume, and temperature should be the same. And of course, the reverse is true. An irreversible process is a process which cannot be taken back from the final state to the initial states. Now, that's enough regarding the isothermal process. Now, let's look at an adiabatic process. An adiabatic process is a process that takes place in such a way that no heat either enters or leaves the system. This is more like an isolated system. Nothing comes from outside. No heat comes in, no heat goes out. That's an adiabatic process. It is simply a process that takes place in such a way that no heat enters or leaves the system. Now let's look at the first law of thermodynamics. Of course, again, the first law of thermodynamics here shows that Q, which is the heat given in, is going to be equal to the change in internal energy plus work done. This is change in internal energy, capital U. But now, since this is an adiabatic process, and the condition for an adiabatic process is that no heat is coming in or leaving the system, it means that as far as an adiabatic process is concerned, there is no change in Q, because there is no heat coming in the system, there is no heat leaving the system. Everything that is inside here is self-sufficient. It is an isolated system. It is cut off from the surrounding. So it means our value of Q there is 0. If this our value of Q is 0, it means that this is 0 is equal to change in U plus W. So meaning the first law of thermodynamics, as far as an adiabatic process is concerned, is going to reduce to change in internal energy is going to be equal to negative work It means that if this gas expands, some energy will be lost in doing external work. So if some energy is lost in doing external work or doing work against the surrounding, the temperature of the system will drop. Conversely, if this piston is compressed, work is done by the surrounding onto the system. Now this compression of the gas causes the internal energy of the system to increase, and as a result, the temperature of the system will increase. So you realize that there's some similarity here with the isothermal process, only that with here there is no heat that is coming in, there is no heat leaving. This thing is on its own. So it means that when we look at an adiabatic process, the PV diagram for an adiabatic process is going to be, it will resemble the one of an isothermal, only that when it comes to a PV, it will be a bit steeper. It will be a bit steeper, but the PV diagram will be the same. So, like also an adiabatic process here, it also has conditions. For you to be able to push this piston down and then the temperature increases, then you pull it up and then the temperature drops, there are conditions that need to be met. Now, in an isothermal process, this thing was supposed to be pushed slowly so that you give time for the heat to move out, and then when you pull it up, you have to pull it up slowly so that you give time for heat to flow in. But then for an adiabatic process, we do not have time for heat to move in and out of the system. So actually, when it comes to an adiabatic process, it's the reverse of the isothermal. For an adiabatic process, you have to push this piston very fast. If you're to compress this gas, compress it very fast. If this thing has to be pulled out, it has to be pulled out very fast. The reason as to why this thing is done very fast is so that we do not give time for heat to flow out or in. We do not give that time, we do not give that allowance. So that is one of the first conditions, that the piston should be moved very fast, or it should be moved rapidly so that there is no time for heat to be transmitted. That is the first condition. The second condition is, like you're seeing, this container has to be insulated. It has to be insulated and its walls have to be thick. The reason as to why it has to be insulated and thick is so that heat cannot be conducted. So in other words, the container has to be insulated to avoid heat loss. On top of that, the vessel has to be thick-walled and poorly conducting. Then the other condition for an adiabatic process to take place is this piston that is moving down should be light and should be frictionless. Now these are the conditions for an adiabatic process. And however, when it comes to an adiabatic process, you need to take note that a true adiabatic process is ideal, or by ideal I mean it's theoretical. It does not exist in real life. However, when it comes to real life, if a gas expands rapidly, then it means that that gas is nearly adiabatic, especially if that gas is contained between walls that are not only thick but also poorly conducting, or whose walls are also poor conductors. Now we may give some examples of processes that are approximately adiabatic in real life. If, for example, a car tire bursts. When a car tire bursts, the air in the car tire escapes out of the car tire very rapidly. When that happens, it means that that rapid escape of air from a burst tire is a process that is nearly adiabatic, though not perfectly adiabatic according to this model. So in our next sessions, we shall explore more on work done by a gas, and particularly we shall look into how to compute work done for some of the processes we have discussed in this session. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia, helping you manifest excellence.